Welcome to The Explainer. So glad you're here. If you've glanced at the news or social media lately, you've probably been absolutely bombarded by AI buzzwords. Neural networks, deep learning, predictive algorithms. It all sounds incredibly complex and, honestly, maybe a little intimidating. But what if I told you that beneath all that complexity, the way machines predict the future is actually grounded in incredibly elegant, straightforward logic? Today, we are demystifying machine learning by looking at the very foundation of how data science works.
So, how do machines actually predict the future? Honestly, when you strip away all the hype, the vast majority of predictions in data science really just boil down to two foundational methods. Whether an algorithm is guessing the future price of a stock or deciding if a charge on your credit card is legitimate, it's almost certainly starting with one of these two basic mathematical approaches. Okay, let's dive into this. Here's our roadmap. We'll look at the two ways to predict, then linear regression for numbers, logistic regression for categories, put them in a head-to-head matchup, and finally, look at the real-world stakes. And don't worry, we are keeping the math super light today and focusing on real consequences.
Part 1. Two ways to predict. Inputs and outputs.
Before we get into the algorithms themselves, let's just quickly sync up on our data science vocabulary. Every machine learning model basically runs on two things: independent variables and dependent variables. Think of it like a bag of groceries. The independent variables are your raw inputs, right? The shape, the color, the weight of the veggies going into the bag. The model is just the recipe processing all that. The dependent variable, that's the final output we actually care about predicting. The label the machine spits out, like, hey, this is broccoli, or the total price of the bag. The output entirely depends on the input.
Moving right along to Part 2. Linear regression, predicting numbers.
Whenever we want our final output to be a specific number, this is our go-to tool. In data science, when someone says regression, they literally just mean spitting out a number. It's a statistical model that predicts a continuous, dependent integer. Imagine you're forecasting the highs and lows of the stock market. Because you're looking for a specific dollar amount, you'd use linear regression. It basically takes a look at your historical data and draws a straight, best fit line right through the middle of it. Now, what's really interesting about this is the core logic driving that line. You probably remember this from high school geometry: y equals mx plus b. Or, in this case, b0 plus b1x. Y is the output we want and x is our input. But check out that error term tagged on the end. The entire goal here is to find a mathematical formula that fits your data points while shrinking that error down as much as humanly possible. It measures this accuracy using a technique called least squares estimation, basically calculating the absolute shortest distance between your scattered data points and that straight line it just drew. Let's ground this with a concrete business example. Say a company is tracking ad spend versus sales. $50 in ads gets them 100 sales. Bump that up to $150, they jump to 275 sales. At $200, they hit 300 sales. Because this data trends upward in roughly a straight line, linear regression is perfect here for filling in the blanks. If the marketing team asks, hey, exactly how many sales will a $175 budget get us? The model just looks at that line and gives a highly educated numerical prediction. In this case, probably right around 280 sales. Section 3. Logistic regression, predicting categories. So what happens when we don't want a number? What if we want a category? Well, logistic regression steps in. And fun fact, despite the name, it's actually a classification algorithm. We are completely ditching the idea of finding an infinite continuous number. Instead, we want a rigid, discrete, binary answer. We need the algorithm to divide inputs into predefined categories. Yes or no, true or false, 0 or 1. Because we're forcing a yes or no answer, a simple, straight line just won't cut it anymore. Instead, logistic regression uses what's called a sigmoid curve, which is this distinct S shape. That curve acts as a very strict threshold. Using a mathematical method called maximum likelihood estimation, it grabs all the data probabilities and shoves them either above the threshold into category 1 or below the threshold into category 0. It essentially forces a very clear-cut classification. And you interact with these models every single day. A classic example: your bank monitoring your credit card. The bank feeds your transaction history, your inputs, into the model, but they don't want a random number back. They want a simple 0 or a 1. 0, totally legitimate charge, let it through. 1, potential fraud, lock the card down. It's the same logic used in image processing, like asking, is this a picture of broccoli, true or false? Or in stock trading, simply classifying whether a trend is pointing upward or downward. Section 4. The head-to-head matchup. This brilliantly illustrates the ultimate dividing line in data science. You can instantly know which model to build based purely on the business problem you're trying to solve. If your problem asks how much or how many, you need linear regression. It predicts integers, uses the straight line, and measures accuracy with least squares. But if you're asking which one, or is it true or false, boom, you switch to logistic regression. It predicts categories, relies on an S-curve, and uses maximum likelihood estimation. It really is that beautifully simple. Finally, Section 5, Real-World Machine Learning Stakes. Let's see this in action.
All right, now for the really fun part. Let's take these abstract concepts and throw them into a real-world Python programming environment to see the stakes. When data scientists actually code these models, they basically follow a standard 4-step recipe. Step 1, import the raw data, like a massive spreadsheet. Step 2, encode the labels. Because computers don't understand text like male or southwest, scientists have to convert those words into numbers like zeros and ones. Step 3, and this is absolutely crucial, split the data. Usually 70% goes to training the model, and the remaining 30% is hidden away to test it later. The model must never see that test data beforehand, otherwise it's just memorizing, not actually learning. And step 4, fit the model to the training data and make your predictions.
Let's look at how this plays out for linear regression with a medical insurance case study. The insurance company plugs in independent variables, a customer's age, BMI, region, and whether or not they smoke. The Python model analyzes all of this and assigns weights. It might quickly discover, for instance, that smoker status has a colossal numerical impact on medical risk. It crunches all these coefficients together and spits out the exact dollar amount the company should charge that specific customer to cover their projected bills. But now let's raise the stakes and test logistic regression. We aren't predicting dollars anymore, we're predicting categories, specifically a 1 for poisonous and a 0 for edible. The dataset here has thousands of wild mushrooms categorized by 23 different features, things like cap shape, cap color, and surface texture. We're asking the machine a simple binary question based on these features. Is this mushroom safe to eat? Yes or no? This is literally a matter of life and death. So the data scientist runs the model, fits the S-curve, and Python spits out an accuracy score of 95%. I mean, wow, right? In almost any other context, passing a test with a 95% is a massive A-plus success. You'd probably think this model is perfectly ready to be deployed into the wild to guide foragers. But here's the crucial point. You can never just blindly look at top-level accuracy. You have to break it down using what data scientists call a confusion matrix, which shows exactly where the algorithm got confused. If we look closely at this matrix, the model correctly identified 121 edible mushrooms and over 1,000 poisonous ones. Awesome. It also labeled 56 edible mushrooms as poisonous. A false alarm, sure. But hey, you just miss out on a meal. But look at the bottom left. The algorithm took 68 highly toxic, actual poisonous mushrooms and confidently predicted they were perfectly safe to eat. This reveals the absolute golden rule of data science. How a machine learning model fails is just as important as how often it fails. A 95% accuracy rate sounds phenomenal on paper until you realize that the 5% error margin is highly concentrated in the one category that will literally kill you. You absolutely have to understand the specific domain risks of the problem you're solving before trusting a machine's mathematical output. Which leaves us with something to really think about. We live in a world that is increasingly governed by predictive algorithms, deciding our credit scores, our healthcare, the media we consume. So, the next time a machine learning algorithm makes a decision for you, will you be satisfied just trusting its overall accuracy rate? Or will you want to look under the hood and ask to see its confusion matrix? Thank you so much for joining me on this explainer. Keep asking those tough questions, and I'll catch you next time.